Welcome to another exciting edition of Hey, That's My Physics. So this is take let's just go with 10. I mean that's obviously a lie, but I apologize if I actually jump over something because I want to be done with this, and yet the computer hates me. So here we go. I mean, some of you might feel that way about physics too, but I get it. Sometimes life happens. So here we go. We got a situation. A woman is holding a rock in a hot air balloon. Why? I have no idea. There. Rock, hot air balloon, starts on the ground. Very exciting. The balloon is released from the ground and immediately travels upward with a constant velocity of 5 meters per second. Oh, also very exciting information. Probably important. The woman then drops the rock. Why? I have no idea, but she did it. And the time it takes for the rock to travel up with the balloon and then fall back to the ground is 10 seconds. So she's going to drop it from some random height here. Apparently, she didn't like the rock. And then the rock is going to begin to fall. And the time it takes to go up and then come back down is 10 seconds. So, fun fact, when she drops it, the initial velocity is still 5. And the acceleration, it's now in free fall, so it's negative 9.8. And to assist me, I'm going to take out my lovely assistant, the velocity time graph. Yes. What, no applause? All right, fine. She's unfazed. So it starts with a velocity of 5, and then goes at that for a nice constant pace. And at some unknown time, again, we have no idea why she did this, but she drops the rock. The drop then plummets down, down, down. We have a wonderful slope of negative 9.8. And at some time, 10 seconds, the objects will reach the ground. So we want to figure out where was it dropped from. And right here, this is the drop. Okay, that's where it's dropped because that's when the velocity goes from being a nice constant velocity to acceleration. And so if we can just figure out what this displacement is right here, we can figure out how high it was before it was dropped. Now, one thing I noticed is that if you throw something up, let me get another color here. If you take something and you take it to this height, well, that height's the displacement. And then when you drop it, well, it's going to keep going up a little bit, and it's going to come back down and land on the ground. So really, its displacement is the same. So the displacement going up and the displacement going down, if you add those two together, it started on the ground. What? No, go away. No, what are you doing? No, 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 no. Work for me. This is why I've been doing this take 10. Yeah, I don't know why. Computer hates me. So you start with a position of 0. You're going to end with a position of 0. So if you look at our two displacements, the displacement going up plus the displacement going down, those two displacements will equal 0. And so that's what we're going to be investigating. So here's the displacement going down. Let's get some red because I'm seeing red. So here's my displacement going down. If I add those two together, I should get a grand total of 0. So I have done this with graphical methods, but I found that kinematics just kind of worked more for me. So here's how I solve with kinematics. First, I'm going to examine the way up. So for the way up, I said, man, that's nice constant velocity. I remember the days of yore. Well, we only had one equation where the average velocity is equal to your displacement divided by your time. And I said, well, let's look at the graph. My average velocity happens to be a big whopping 5. Ooh, very exciting. And then my displacement is what I'm trying to figure out. And my time, well, it's really only this for this time t. So that is my first thing. Now, I'm going to rearrange this just a bit because I want to solve for displacement. So delta x equals 5t. So that's on the way going up. So now, going down is the hard part. Falling. Usually that's the easy part, but oh well. When you're going down, I'm going to list my givens. I happen to know information about this spot here, so I know that my initial velocity is 5. I know that my acceleration is negative 9.8, because that's the slope of my velocity time graph. I also am saying, man, what's that displacement? I have no idea. And then my time, and this is the key part. The time is actually 10 minus what we defined as t. All right, so my time is actually, this is the time interval at which I'm looking. So 10 minus t, that's my time interval. And so I say, hey, these are my variables I'm concerned with. Only one equation will fit the bill to solving my problem. And of course, it's the simplest of all equations. That was sarcasm. I'm working on it, I know. So you saw that's the equation I'm using, and we're going to have to solve with it. So I've put down my thinking all over the place. I've chosen another model, and now I'm going to substitute information into there. So the delta x is still an unknown. My initial velocity is 5. My change in time is 10 minus t. Oh, this is not going to be pretty. Plus 1/2 acceleration, negative 9.8. Then time is 10 minus t quantities. Oh, oh my goodness. Oh my, hold on. We may need to take a station break here because algebra is going to come and attack us. So we're going to take a momentary station break and let algebra magically appear. Oh my goodness. Oh, there we go. Every time algebra appears, it scares me. All right, so again, if you want to walk through the algebra, there it is for you. You can pause the video, check it on your own. I'm sure it's riveting stuff, but basically you do a bunch of algebra, simplify, and you then get that answer. And the question is, well, what do we do with this now that we have it? Well, up here we talked about the fact that our total displacement, our up plus our down, is going to equal 0. So that's what I'm going to do now is I'm going to come back and combine these. So if I add these two displacements together, that should equal 0. So 0 is going to be equal to 5t plus all this stuff over here, 93, you do this, minus 440. And then I can simplify that even further. So when I simplify that even further, I get negative 4.9 t squared plus 98t minus 4t. And now it's quadratic time. That's right, folks. Bust out your quadratic solvers or your graphical calculators, however you want to solve it. Go nuts. But when you do that, you'll discover that you get 2 times, as usual, because of the quadratic nature. 6.8 seconds as an option. And another option is 13.2 seconds. So now you got to use your noggin and ask yourself, well, which one's viable? And 13.2 is definitely not viable because we only gave ourselves 10 seconds total. So this guy cannot be one of our answers. So that means that this guy is the time it takes to rise to our max height. That's our t that we solved for up here. So now if I want to figure out that max height, well, if you look, it's a nice simple rectangle over here, so I can calculate the area. So I'm going to just go back and use this equation here. And so I'm going to replace my t, where I have my displacement equals 5t. I'm going to replace that with delta x equals 5 times 6.8. That's how you draw 8s. And figure out that my displacement is going to be 34 meters. Well, isn't that nice? So that, my friends, is my final answer, final solution as to the height that the rock was dropped from. So that's how you solve it. I know that the algebra may seem a little intimidating, but fundamentally I said, you know what, I've got a nice graph and I've got 2 types of motion and I've got constant velocity here and I've got constant acceleration here. And I said, you know what, I've got graphs that can describe these, I've got equations that can describe these, and I've got some known physics understanding. And just kind of put it all together and I saw where it took me. And that's basically what I want to emphasize here, is that you don't have to go in saying, well, obviously you must do this. You go in saying, man, what can I get? What information can I get out of this? And let's see where it takes me. All right? So, as always, have fun with physics.